to the second question?
Yeah.
Okay. Let me just show you one thing else. So about the dominance between these two EMVs. So I go to, when I run the simulation, I go to this cumulative ascending, which fits a cumulative probability distribution graph to the distribution of each of these EMVs. So I have it for EMV of A, and then I can go to this option where I can add overlays to this graph. So I click on this, and then say I want it for both outputs. This way I have this cumulative probability distribution function for both outputs that I have here, and then I can do the interpretation about any dominance relation if there is any between these two. So
B would be dominant, right?
Yeah. So it seems that D is almost dominant. So here at the end, there's some crossing, but it's very minor. So overall, I can say B, which is to the right of strategy A, the graph, is dominating A, because in this case, I'm maximizing this profit or the EMV value, and I'm looking for a graph or distribution function here that results in higher probability for higher profit values. So for each of these values that I have on this horizontal line, if I put a vertical line to read the probabilities, it seems that for each value that I have here, the probability of ending up with that specific value or lower values for B would be lower, which means the probability of getting higher profits would be higher for B. And because this is a maximization problem, I'm looking for higher probabilities for higher profits values. So the general rule would be, if you're maximizing a problem, the one on the right or underneath the other cumulative distribution function lines would be the dominant. But if you were minimizing this problem, so you will be looking for the one that is above all other lines. I already discussed this with you, but in this case, because we are maximizing, I'm looking for the one that is under other lines. I just have one more, so B seems to be almost the dominant strategy here. Any questions?
Can we continue?
All right. So the third question is about calculating the expected value of perfect information if you are hiring an expert just for A. So it seems that we can get rid of this A uncertainties if we are hiring the expert, but we'll still have the uncertainties related to B. So I put the tree and then see how the tree looks like if we have an expert for A. So the initial node would be a decision node of hire experts for A, and then the second one would be do not hire experts. If I do not hire any expert, the problem would be the same as what I already have. So initially it would be the decision between A and B. And and then I put the uncertainties for each.
I mean,
For
do I
A,
have
I
everything?
have 3 uncertainties.
Yeah, I got you, bro.
So I add one more. A1, A2, A3. The probabilities are 60, 25, and then 15. I have the monetary values, 20. Minus 10. And then B would be 2 outcomes. B1, B2. Probabilities are 70, 3, okay, so this is the original tree, but what if I hire an expert for A? So if I hire an expert for A, I initially start with an uncertainty node with 3 outcomes because A has 3 outcomes. And depending on whether the expert says outcome 1 would happen, outcome 2 would happen, or outcome 3, I need to make a decision between A and B. So this is what expert says. Expert says A1, expert. So this is expert says A2 happens. Or so the probabilities is 60, 25, and then if the expert says A1 happens, because I'm assuming this expert has perfect information about A, so A1 will happen for A for sure. But for B, we'll still have the uncertainties. So I put the decision node here for A and B. For A, the outcome would be A1, so I insert here where I defined A, and then put the monetary value, 20. But for B, I will be inserting an uncertainty node. B1, B2. 70%, 30%, 20, minus 1. Any questions? Yeah.
So we're not hiring so we have to still include B, even though
Yes.
we're looking just at A.
Yeah. So you are consulting an expert for A, but because you have your initial decision on whether to go with A or B, you have this uncertainty.
So we still have the option open for us to still choose B.
Yeah.
We're the same.
Exactly,
Okay.
yeah. But the expert gives you some visibility about what is going to happen to A. For when the expert says A2 happens, I make here a decision between A and B. For A, I know the outcome would be A2 for sure, so I answer 10. But for B, I will be having the same uncertainty. So I just copy that and then paste it to this last node because it's the same. And then when expert says A3 happens, so A would be, the value for A would be minus 10. And then B. And then I paste the same subtree for B. Yes.
How did you decide when the expert says 60%, 25%, 50% chances for the A1, A2, A3? Because I get that those are the probabilities and those
Yeah.
should be the outcomes, but
So, yeah, so this is, so based on historical data, you know that in 60% of the times, scenario A1 would happen before,
Yeah.
before consulting expert. And then that's what you're using for saying, okay, because I know A1 is happening with 60% of chance.
Yeah.
So there's also 60% of, before going to the expert, there's also a 60% chance that expert would also say that A1 happens. So this is my estimation of what the expert would say.
is that the way all these EVPI problems happen? Because I feel like I remember an example where the expert says specific probabilities for each one. Like, is this always the way it goes?
Yes.
Okay.
But in this case, we are assuming the expert has perfect information, but in the base question that I gave you for exercise, the expert didn't have perfect information. So here in this case, when he says A1 happens, I know exactly A1 happens. But if that expert didn't have perfect information, I could also have some other uncertainties,
Right.
or whether he's right or not.
Yeah.
But in this case, we are assuming that the expert has perfect information.
But if you had imperfect information, you would just turn those
Yes.
the
So,
outcome to a uncertainty and then put the B uncertainty in as well.
yeah.
Okay.
Because the uncertainty for B is still there.
Yeah.
Because I'm not consulting any expert, I'm not supposed to consult any expert for B. Okay? So the expert just helps me with A.
Yeah.
Okay. So in this case, if I go with an expert for A, let's just the EMV value would be 17.48, but if I don't go with an expert, the EMV value would be 13.7. So because the EMV, if I hire an expert, is higher than the EMV, if I don't hire this expert, it's good to consult this expert. Because overall, it will result in a higher EMV value for my problem. And in this problem, I'm maximizing this EMV, so it's better to consult this expert. If it was a minimization problem, and you were minimizing the expected cost value, you will be looking for the decision that is resulting in a lower or the lowest EMV value. But in this case, the EMV of hiring an expert is higher, so I would be better to consult this expert. And the EVPI in this case would be this value. EV would be the expected or the EMV of consulting experts minus EMV of not consulting experts. So it's a positive value. Any questions so far? Yes.
So on the test, are you going to be like, you want to maximize or minimize?
It depends on your problem, yeah. So in this problem, you're maximizing.
Mhm.
So so it's better to consult experts because the EMV value is higher.
Okay.
But if it was a minimization problem, it was not good to consult this expert.